So, 9-2 notes, part 1, redox half reactions. Again, we started with this a little bit last week with some half reactions. And we also started with this main tenet of redox. We know that oxidation cannot occur without reduction and vice versa. We have to have both of them. That's why we summarize it with a redox reaction. You can't have one gaining without another thing losing. When we write a half reaction, we see the two parts of the reactions individually. And that helps us understand this concept of two different things are going on. When the two half reactions are balanced and added together, we get the complete reaction, what's actually going on, minus most of the time anything that we have that is just an onlooker. What did we call that before? No. The ones that are just there. They're not doing anything. The oxidation number doesn't change. It was our second homework question that we had today. The hydrogen. What did we call that? It's like when you go to a game but you're not playing the game. Spectator. Thank you. So the spectator ions we wouldn't have to write because they're not actually involved in any of the oxidation or the reduction. So our final reaction quite often does not have those. Just like question 1 on our homework assignment where we already had the oxidation numbers written out because there were some other things bonded in there that were only spectators. Their oxidation number didn't change from one side to the other. I see a couple of you writing that. That's good. Okay. First example here. This one's one type of way of looking at these overall redox reactions. And in this one, chlorine and iron are going to react to form a compound at the end. So the two half reactions that I have the oxidation half of the reaction where iron turns into the iron ion because it's bonded to something else. And I put 3 electrons there. I'm going to tell you why in a second. So a few things. I know from many balancing of equations that I have to have the same number of things on each side. So sure enough, I have iron, one of them, 1 mole of them, on the reactant side, 1 mole of iron on the product side. So that part of my equation is balanced already. Good so far. The thing that is not good so far are my charges. I need to make sure that not only my elements are the same on each side, but also that my charges are the same on each side. The only way that I can change the charges is by adding electrons. So that means I am going to pick whichever side has the lowest oxidation number to try to meet on both sides. So I've got 0 on my reactant side. Before I put the 3 electrons in, I had a positive 3. Obviously, the one that's less is 0. So I need my product side to be 0 as well. And that is why I have added 3 electrons to it. That way I have a 3 positive and a 3 negative. So I have 0 overall on both sides. It's one of our key things to balancing half reactions. The sum of the charges on each side must be equal, not necessarily 0, except in this case.
Where did the 3 plus come from?
That would have been given to you.
Okay.
You'd have to know. Good question. Okay, so looking at my reduction side, I have Cl2. Why is it a Cl2? It is diatomic, absolutely. So chlorine, when it's not bonded to something else, is a 2. There's 2 of them. Why did I not have Cl2 on the product side? Do you know, Noah?
Because that is the coefficient of 2.
We put the coefficient of 2 in because we needed to get it balanced. That's correct. The negative is telling us that it's bonded to something. It's not telling us what it's bonded to right now. Sometimes it's a spectator ion. In this one, it's going to be the iron when all is said and done. But it's bonded to something. That's why it's an ion. We just don't see what it is right now. And Noah's absolutely correct. We put the 2 coefficient because I have 2 moles on the other side. I need 2 moles on this side. And I look, before I put my electron there, I look at my charges, my oxidation numbers. The Cl2 is a 0. I have 2 1 negatives on the product side. So that means my electrons have to go on the reactant side. I need 2 electrons so that I have a 2 negative on each side. So my elements are balanced, my charges are balanced. One thing you might want to write down to help you remember, and we did this on our chart the other day, the oxidation reaction, since it is losing electrons, we write the electrons when we're balancing on the product side. We see it anyways when we're doing it because we can see that we need to match up the charges on both sides. But if it's helpful for you to memorize facts, if it's oxidation, a fact is that the electrons will be on the product side. And the fact is that if we are having a reduction half of a reaction, the electrons go on the reactant side. And that one's kind of nice for us. Reduction, reactant, they both start with re. So on the reduction, when it's gaining electrons, the electrons go on the reactant side. I'm going to treat these kind of like I did with Hess's law. When I was dealing with enthalpy and I was trying to figure out, I was trying to get to a target equation. Get like 3 equations, and I said, I want this equation at the end, and I want to know how much energy it has. And I did things like flipping them around or multiplying them by a number so that I could get that target equation. That's what I'm going to do here. I'm going to get these 2 added together in such a way that I get a final equation. I'm just not given the target equation this time. I determine the target equation. One of the things to be able to do that, though, is that when I add them together, I need the electrons to be able to cancel each other out. Question, Sean? Okay. Do a big star by this, or write it to the side, that you cannot write a final equation with electrons. They need to cancel out. If they don't cancel out, you did something wrong. So if you have electrons in your final target equation, you need to go back and fix it. So in this one, I have electrons on the product side. I also have electrons on the reactant side. They're not the same number, though. If I were to add these equations together, my 2 on the reactant side would go away, but I would still have 1 on the product side, because 2 of them would cancel out on both sides, but there'd be 1 left over. So this would not be written correctly if I just added them together the way they are. So I have to do a little bit of something, like I did with Hess's law, to get things to be able to cancel out. They need to be the same on both sides. And I see a 2 and I see a 3. I've done a lot of balancing this year. So if I see a 2 and a 3, what should my target number be? 6, absolutely. So my first equation, I'm going to have to multiply by 2. And just like we did with Hess's law, the entire equation gets multiplied by 2, not just the electrons. If I do something to one of them, I have to do it to the whole thing. Product side, reactant side, all of it. My other equation, I have 2 electrons, so I'm going to multiply that entire reaction by 3. 3 is multiplied by the Cl2 plus the 2 electrons plus the 2 Cl1 negatives. And I can rewrite it once I distribute. Get 2 Fe goes to 2 Fe3 plus 6 electrons. And then 3 Cl2 plus 6 electrons goes to 6 Cl1 negatives. And I've got extra brackets on the end of both of those. I apologize, you don't need those brackets on the end. Will my electrons cancel out now? Yes! I love to see so many shaking heads. Yes, absolutely, they will cancel out now. That is very good for us, because now we can add it together. Just like I did with Hess's law, all of the stuff that's on reactant sides are going to be on my final target equation reactant side. Everything that's on the product side is going to be on the final product side. So, I'm going to have the 2Fe plus 3Cl2. Here's one thing that is slightly different from a lot of them that you'll have. I said in the initial part of this that we get a compound in the end. I have a precipitate formed, and that's why they're both solids here. It's telling me that, hey, you're forming a compound. So I'm going to write down that compound. Iron is a 3+, chlorine is a 1-. Crisscross, like I have all year. I get FeCl3. So my coefficients are going to change a little bit. I get 2Fe plus 3Cl2 goes to 2 FeCl3s. So I still have 6 chlorines, but since it's in this compound and I've crisscrossed, I have a subscript of 3. So 3 times 2 is 6. I still maintain that 6. It's just in a slightly different way of writing it because I do have a compound. Again, you have to be given some sort of information that it's a compound. Either in the question it'll say it forms a compound, or you see here that it's solids. Solid plus gas goes to a solid. That means a compound's been formed. Sometimes you're going to have ions at the end, beginning and the end, or just the beginning or just the end, because of spectator ions. What questions do you have before we move on to example 2? Okay, so looking back at half reactions in general, the most simple type of half reactions that you're going to have are either single displacement or double displacement. And it could be either a single displacement or double displacement that one involves the displacement of ions from one metal by another metal. So that means as a spectator ion I would have a halogen or another nonmetal. That's what it's talking about in number 1. I have a single displacement or a double displacement with a spectator ion that is a nonmetal. Number 2 involves a single displacement or a double displacement that involves a halogen displacing the ions of another halogen. So in this one, my spectator ions would be a metal of some form. So my metals are not going to be written down. They're just in solution. And they're being moved around. We are going to get to slightly more difficult, or not majorly difficult, but slightly more difficult ones tomorrow with those notes, where it's not quite so few steps. Okay, here's our second example. I have an oxidation reaction where magnesium is turning into Mg2 plus 2 electrons. Again, since I am losing electrons, it goes on the product side. Oxidation is the loss of electrons. It goes on the product side. The reduction half of my reaction is already balanced out for us. So normally I would just have Ag plus electron goes to Ag. But again, it's already been balanced out for us because I know I need 2 electrons that are going to be able to cancel one another out. So I multiplied my entire equation by 2. Question? Okay. So, my magnesium plus my 2 silvers form 2 silvers plus my magnesium ion. There'll be clues for you. It'll not always. No. So what this is saying is I have a single displacement reaction. You might want to write that down. Single displacement reaction where I have some non-metal spectator ion. So I could write it just as easily with, let's say, chlorine. So magnesium is put into a solution of silver and chlorine, silver chloride. The magnesium comes in, kicks out the silver. Silver is now on its own. This would be a fun way to make some silver. Probably not an efficient way, but it would be a way. The magnesium now is bonded to my spectator ion, which I picked randomly as being chlorine. So this is really magnesium chloride, MgCl2. But again, since this is a spectator, it doesn't matter for me. Could have just as easily been iodine. Could be oxygen. Doesn't matter. And that's why it's not written down. But it's important for you to be able to look at this and say, single displacement reaction. My spectator is a nonmetal. Being able to say those two things is important. Knowing what's going on the molecular level is important. Here's another one. My equations are not written out right yet. Look at them. Once you have identified what's written incorrectly, give me a thumbs up. And it's not a race, so look over it carefully. Once you have identified what is incorrect, give me a thumbs up. Okay, Owen, where's my mistake?
You don't have chlorines on the
Side. Absolutely, yeah. So there should be a 2 as a coefficient in front of the chlorine there. Because I only have 2 chlorines on this side, or I have 2 chlorines on this side, I only have 1 on this side. So it should be 2 Cl1 negatives. And that makes more sense with the charges too. I have 2 electrons here plus a 0, so I have a -2. If this was just a -1, that wouldn't be right. Do I have the correct number of electrons in both of them? Yeah, can I cancel out my electrons in both of them? Yeah, so I get 2 Br1 negative plus Cl2 goes to Br2 plus Cl1 negative. This again is a single displacement reaction. This time, my spectator ion is a metal. So this is like the second type of the most easiest ones that we can deal with. The last one was the first type of the most easy that we can deal with.